Hey folks, I wanted to try to give you a overview of linear regression and residual plots. So here we go. First thing is one of the reasons that we do a scatter plot in the first place is because we think maybe there might be some association between something and something else. And if there's two things we're comparing, we have to ask ourselves which one should go on the x-axis and which one should go on the y-axis. And I think we should have pretty good reasons for doing one or the other. And I'm going to tell you my reasoning right now. What you want to do is you want to think about, is it possible that one variable is responding to the other? And if that's the case, that's the variable that should go on the y-axis. Now, I'll admit to you, it's not always clear. Sometimes we don't believe that one variable is responding to the other. We just want to see how they relate to one another. But in general, we're looking to see, does one variable respond to another? And if it does, then we're going to put the response variable on the y-axis. Also, when we have to put the data into our graphing calculator, I think there is some confusion about where do we put the data, which data do we put where? And in general, we're going to put the data that goes on the x-axis in the first list and the data that goes on the y-axis in the second list. So it's just kind of nice because it's orderly that way. You know, x data first, y data next. And so when you go to configure your plots, or when you go to do linreg on the graphing calculator, you go to choose your x list and your y list, hopefully your x data is in list 1 and your y data is in list 2. Of course, you can use any other lists that you want, but make the x the first list and the y the second list. The line of best fit. One of the things that's confusing about the line of best fit is that it has so many different names. And it's really important that you're clear that all these names mean line of best fit. So let's just go through a few that are commonly used. A lot of times we'll call the line of best fit a regression line, and I'll talk about that in a little bit more. Also, we'll call the line of best fit the least squares line. And there's a really good technical reason for why we call it the least squares line, and I'm not including it in this lecture. My intention is to give you an overview, and my hope is that I'm helping you to fill in details with other presentations. Also, when you go to work with some software and you try to develop a line of best fit, the software will refer to the line of best fit as a trend line. Now, when we talk about graphing things, a lot of times there will be the actual physical graph of something, and then there's an equation that relates to that graph. And a lot of times we'll refer to the equation and the graph as though they're synonyms. In other words, whether I'm talking about the graph or the equation, I'm still interested in kind of the same thing. If I talk about the slope of the graph, well, the equation may have a slope also. And if I'm talking about the y-intercept of the graph, the equation has a y-intercept also. So the two are related, but they're not exactly the same. And and by the way, we can use lines on graphs and equations to make predictions. And that's one of the reasons why we study graphing and regression and lines of best fit, is because we'd like to make predictions. Okay, so graph versus equation. The names above tend to be the names that we use when we're referring to an actual line on a graph. But of course, a line of best fit can also be described by an equation. So let's talk about the regression equation. Again, several names. We could call it a regression equation. We could call it the equation for the line of best fit. And sometimes I'll just call it the line of best fit and I'll be referring to the equation. Also, we can call it a prediction equation. Now, since I'm using the word regression, I thought maybe I'd talk a little bit about what is regression. And this is a definition that I found on the internet, and I kind of massaged it to my own liking. And I think it's a reasonable definition. Regression is basically just an approach to modeling the relationship between an explanatory and a response variable. So when we talk about a regression line or a regression equation, we're just saying that hey, we have all these dots scattered all over the place on this graph, and if we want to use a line to model that data, we'll call it a regression line, because the line itself is an attempt at modeling the data or summarizing the data with one nice clean line. Oh, and another way to think of it is a regression line represents the average trend or slope of points in a scatter plot. In other words, if you have dots all over the place, that one smooth line is a way to sort of represent where the where the dots are going on average. Now, lines of best fit and regression equations can also be described as linear models. And there's all kinds of models, by the way. There's quadratic models, there's exponential models. Right now we're going through the coronavirus crisis, and certainly the number of cases of coronavirus is going up at an exponential rate, and same with the number of deaths, and it would not be appropriate to use a linear model for that data. It'd be more appropriate to use an exponential model. But again, whether it's an exponential model or a linear model or a quadratic model or one of many other kinds of models, a model just means a way of summarizing data points on a scatter plot with a line or an equation. So let's see here. A linear model. Let me give you some words, maybe for those of you that would like to see the words. A mathematical model is an equation or graph that can be used to describe a pattern in observed data, and it can be used to make predictions about values of future data or to determine values of past data. So we, for instance, with coronavirus, we're curious how many people will be infected with coronavirus in the coming months. But at the same time, we use things like carbon-14 dating to determine how old some bones are that we find when we're on an archaeological dig. So mathematical models can be used to make predictions about the future and also tell us things about the past. Okay. Oh, and I had an example here. There's actually a relationship between the height of a human and their wingspan or their arm span, and it's a pretty linear relationship. So we could say a straight line would be a good model for this data. If we go into Naviance and we look at the graph of GPA versus, for some reason I lost the end of this. It should say GPA versus SAT score. If you go into Naviance and you look at the graphs of GPA versus SAT score, and we're going to see them in a minute, you'll see that a straight line would be a good model for the data. But a straight line is not a good model for all data, and that's one reason why I'm giving you this lecture right now. So, is a linear model appropriate for height versus arm span? Well, look at the scatter plot and look at the line. The dots in the scatter plot are all relatively close to a line, so I'd say a linear model is appropriate. Then again, a while back, we looked at manatee deaths and speedboat registrations. Sadly, it was kind of a sad topic to look at. And in this case, too, it looks like a linear model is appropriate. Sometimes a linear model is appropriate, sometimes it's not. But in this case, it sure looks like you could put a straight line through this data, and that most of the dots would be pretty close. Maybe we have an outlier over here. Now, take a look at this. This one's a little different. Here we have the distance from the sun versus the orbital speed of a planet. In other words, how fast does the planet make it around the sun? We'll call that the orbital speed. Well, what is the speed the planet is going as it travels around the sun? Well, it turns out that the farther you are from the sun, the slower the overall speed, and the closer you are to the sun, the faster the overall speed. So so in this case, a linear model is definitely not appropriate. Now, take a look. Here is a graph from Naviance, and you can see it is a scatter plot of, down here we have SAT scores, and up here we have grade point average. And you can see that it looks like a straight line would be a pretty good model for this data. Here I'd say a linear model is appropriate. If we graphed the fuel used versus car speed, we get a really interesting looking graph. It looks like something like this. In other words, there's kind of a sweet spot for how fast you go and the fuel mileage you get. If you go too slow, you use a lot of fuel without going much distance, and if you go too fast, you use a lot of fuel. You know, even regardless of the distance. But there is kind of a sweet spot. Here, the data has a very strong association. You can see that, and the same with the planets and the orbital speed. But even though the association is strong, a linear model is not appropriate, and the correlation would not be very strong here. In fact, you can see the R value, which is the correlation coefficient, is relatively low. It's pretty close to 0. So in this case, a linear model would not be appropriate. So, when is a linear model appropriate? We use 3 things to evaluate that. 1, we use a scatter plot of the data. 2, we look at the correlation coefficient R. And 3, we look at a residual plot of the data. Now, what happens is when you're out in the field working on things, you have to use your experience and critical thinking along with these 3 pieces of evidence to determine whether a linear model is appropriate. So, something weird happens when we have very little data. When we have very little data, it's a little harder to interpret what's going on. But here is a graph on a graphing calculator. It's a scatter plot with a line of best fit. And I want to help you with the interpretation here. It does look like the dots are not exactly on the line, but people, I have to tell you this. In life, it's going to be rare that you come across data where the data points are as close to any line of best fit as these points are here. So, oh, by the way, I just noticed that you could maybe just barely see me there. Don't want to pull myself out of there. Anyways, so I would say that in this case, my interpretation of the data here is that there is a very strong correlation between the x variable and the y variable in this case. There must be, because the dots are all almost perfectly on a straight line. Now, this only makes sense in context, so we need to really compare it with something so you can see a case where maybe the correlation is not so strong. Anyways, in this example of a scatter plot, it looks like a linear model is appropriate. And we normally describe a scatter plot using strength, direction, and form. And so let's look at some examples and talk about strength, direction, and form. In this grouping of 4 scatter plots, the top right one is the easiest one to identify. It's got a very strong correlation between the x and the y variable. And that is the strength of the relationship. The direction is positive as opposed to negative or none at all, and the form is linear as opposed to curve. The bottom right one, this guy over here, it looks like it has no correlation at all. Now, if you look at the 4 possible options, what you'll see is that it is one of these, but it's probably going to be like 0.26. So that should give you a rough idea of what kind of correlation value really isn't too meaningful. And in this case, I would say that a linear model is not appropriate. Even though the computer will calculate an R value, you can look at the scatter plot and say a line of best fit ain't going to be very useful. You could make a horizontal line that represents that data, or a vertical line, or maybe a positive sloping line. Negative sloping doesn't look that realistic, but there's definitely a bunch of lines that could fit this data, and so therefore having a linear model doesn't make much sense. The top left is what we would call a moderate correlation between the X and Y data. The strength of the relationship is moderate. Those dots are not all directly on a line. That's moderate strength. Okay, and by the way, this guy over here I would call weak strength. But something like this, where the dots are right on the line, very strong correlation. Again, here the direction would be negative for the top left guy, and the form would be linear as opposed to curved. Let's keep going. Let's take a look at some more examples so you can really nail this down. For this data, the sun versus the orbital speed, the strength of the relationship of the association is strong. I mean, if you drew a line through these dots, those dots, if you could figure out the curve that goes through those dots, they'd all be right on it. It really looks like there's a strong mathematical pattern there. And maybe you could say that the direction is negative. I'd say mostly it is, but the form is definitely not linear. It's curved. This guy here, very strong correlation between the data. You could come up with a mathematical model that would fit this data. However, it's not a straight line, it's curved. So the correlation you can see is relatively low, because correlation relates to how straight, whether or not the data conforms to a straight line. And in this case, because the data goes down and up, we can definitely not say whether the direction is negative or positive. I would say that there is no direction here. Okay, this one would be, again, maybe a little fuzzier. Here, you could use a straight line to model this data, and you would say that the direction is positive, not negative, and you would say that the data is linear. There's no obvious curve in the data, and I would say that because the data is a little spread out, this is what I would call a moderate strength or a moderate correlation. Not like the dots that you saw in the graphing calculator a while back. That was a very strong correlation. Now, here is a scattering of dots, and let's talk about the strength, direction, and form. It looks to me like the strength is weak. And as far as direction, I am not sure. It kind of looks like it's all over the place. And it's not linear. It's definitely a one straight line. It would not represent this data well. Notice, though, that the computer is happy to put a straight line through the data. That's why we also need the correlation coefficient R, and we also need a residual plot. We need 3 pieces of evidence to really decide whether a linear model is appropriate. So let's talk about correlation coefficient for a minute. Check this data out. And by the way, let's talk about correlation coefficient and what it really is. The correlation coefficient is limited in values. It can only be between 0 and 1 for data that's positively correlated. And it can only be between 0 and -1 for data that is negatively correlated. So it can't be like a million different values. If you have a number of a correlation value that's very close to 1, we'll call it a very strong positive correlation. If you have a number that's very close to -1, we'll call it a very strong negative correlation. If you have a number that's more like 0.7, that's going to be more of a moderate correlation. And if you have a number that's between 0 and 0.25, that's almost no correlation. And even in this case, when you look at this graph with an R of 0.45, it almost looks like no correlation to me. It's a pretty weak correlation, I would say. And again, in general, 0.25 to 0.5 is a pretty weak correlation. These are just rules of thumb. You will have to use your experience and critical thinking and the context of the problem to really decide for a given situation. Okay, now, another thing that can be rather confusing when learning about how to analyze the whether a linear model is appropriate is this thing called a residual plot. There's something called a scatter plot, and then there's a residual plot. And the two things are very different, and there is a different meaning and a different usage behind both of them. And you graph them both differently. When you do a scatter plot, you're literally graphing the x and y values for your data. And whatever the data is, you check and see whether a line of best fit seems to match the data if you're analyzing the data. The residual plot is different. The residual plot is just the difference between every single actual data value and the predicted data value on the line. And when we say actual data value, I mean actual y values, okay? So residuals are the difference between an actual y value and the predicted y value based on the line of best fit. The actual y value and the predicted y value based on the line of best fit. Residuals can be positive and negative. A residual plot cannot be positive and negative. Residual plots mainly conform to two categories. Now, when you go to a more advanced statistics class, you'll talk about more ways to consider residual plots. But we're going to think of residual plots in two ways. One, they have a rather random pattern, which means that a linear model is appropriate. Or two, they have a rather distinct pattern, which means a linear model is not appropriate. And that's how we're going to generalize in this class. Here, in this case, when we plot the residuals of this data over here on the left, when we make the residual plot on the right, the graph that we get looks rather like the data is rather randomly spread above the x-axis and below the x-axis. And for that reason, we will say a linear model is appropriate for this data. This residual plot is the clue that a linear model is appropriate. Now, let's contrast and compare that with something where a linear model is not appropriate. Whoa, here's a lot of data. So in this case, if you take a look at this residual plot over here, residual plot B is the kind of residual plot you would get when a linear model is not appropriate. There is a distinct curved pattern here. And it turns out that this residual plot goes with this scatter plot number 3. You can see, and by the way, in scatter plot number 3, if we computed an R value, I bet you we get a pretty good one. Maybe 0.7, maybe 0.8, something like that. And you might say, wow, there's a pretty strong correlation there, and maybe a linear model is appropriate. However, when we go to do the residual plot, we get more data, we get more evidence, and that helps us to decide whether a linear model is appropriate. And in this case, we say no. Now, again, in a more advanced statistics class, you might run into patterns where you have a residual plot that looks more like D here. And again, for D, we would say maybe a linear model is not appropriate. And it happens to go with Scatterplot 1. And again, maybe in Scatterplot 1, maybe with your good old eyeball, maybe you recognize that a linear model is not appropriate, or maybe you think it is. It looks to me like a linear model might not be so bad. But the residual plot tells us we got to think again. In this class, we're going to try to focus more, though, on whether the residual plot looks like this one. By the way, the residual plot A looks like a linear model is really appropriate, and it just so happens to go with the scatter plot of the data in Scatterplot 2. All right, let's look at some more examples. I feel like even if you don't get it yet, the more examples you see, the better off you'll be. Okay, so check this out. Over here on the left, we have a scatter plot, and then we have the residual plot that goes with it. Here we have a scatter plot, and then the residual plot that goes with it. And here we have a scatter plot and the residual plot that goes with it. These are kind of interesting. In the first example, the data itself, the scatter plot itself, looks like maybe a linear model is appropriate. When we go to do the residual plot, it confirms our suspicion. In the second graph, the scatter plot looks like maybe a linear model is appropriate. But when we go to do our residual plot is strong evidence against using a linear model. Now, the residual plot does indicate that there is a strong correlation between the x and the y variables. I'm sorry, not a strong correlation, a strong association. We're going to use correlation to talk about whether a linear model is appropriate. So there is a strong association between the x and the y variables here, but it's not a strong correlation. It's not a linear model is not appropriate. And in the last graph, what we can see is that you could put a line through the data, and you do get a rather randomly scattered residual plot, but when you look at the original scatter plot kind of tells us that a line of best fit or a linear model might not be the best here. It really looks like there's not much of a correlation. And even if we had our computer calculate an R value for us, what we would discover is that it'd be a really low R value. Okay, we did it, people. Wow, this video went on and on forever. I apologize for making such a long one, but I wanted to give you what I hope is a really strong overview of linear regression and residual plots. I hope that this helps you to do better on future assignments.